Hello everybody, I'm Matteo Cardaioli and today I'm gonna present our work Your PIN Sounds Good, Augmentation of PIN Guessing Strategies through Audio Leakage. Before starting, let me briefly introduce myself. I am a PhD student in Brain Mind and Computer Science at the University of Padova. I am member of the Security and Privacy Research Group of the University of Padova, and I'm a project developer for GFT. My research mainly focuses on behavioral biometrics and detection of patterns of suspicious behavior, authentication, and predictive security of critical financial infrastructure. But let's start with the presentation. In this work, we want to analyze the security of the authentication system currently most used in the banking sector, the authentication via PIN. PINs are commonly used in ATM transactions, post-payment, cell phones, and as a second factor authentication in internet banking, for example. We have been wondering, to paraphrase this sentence by Thomas Jefferson, are all PIN created equal? There are basically two ways to assign a PIN. The first is let the user choose the one he prefers, and this gives good usability to the user. The second is assign it randomly. But to go back to our question, the answer is absolutely not, and we will see it in the next slides. So let's start with the user-chosen passwords. 4IQ is an US company with office in California and also in Europe, in Spain. And they work mainly on cyber attacks and data breaches. And a couple of years ago, they discovered, scanning the dark web, a file with more than 1 billion credentials in clear. They verified that none of them were encrypted, and most of them has been verified as true. But what about PINs? Well, there are no public available PIN datasets, but PINs can be considered as numeric passwords of length 4 if we consider US PINs, or 5 if we consider European format. And since our study has been conducted in the US, we extracted from the dataset only numeric passwords of 4 digits length, and we evaluate the frequency of each PIN. These are the results, and as we can see, there is a certain recurrence in the choice of the PIN. 1234 has a frequency of 9%, then there are 111 and 000. Special attention must also be paid to the 1989 PIN, and if you notice from the graph, it's possible to identify a large number of common pins in that area. This is because users, to remember their PIN more easily, use their date of birth or the date of birth of their son, daughter, and so on. The fourth most common PIN is 1342, and it seems an anomalous sequence in this context, but we assume that it's due to a reuse of the password 1234. Here there are the best 10 pins, and as we can see, they have a very low frequency, but there are a lot of pins in this with this frequency. So in this scenario, 20% of pins can be guessed trying the 20 most common combinations. And if these 20 4-digit pins were distributed randomly and uniformly, they would represent just the 0.2% of the total. So to avoid this eventuality, the best choice is to provide randomly generated pins. If all pins were randomly assigned, there would be no vulnerability on the frequency of use. Each 4-digit pin would have a 1 in 10,000 chance of being guessed, and the security would be given only by the length of the pin itself. But we wonder, are all the randomly assigned pins equal in terms of security? The pin pad configuration and the physical distance between keys could be a vulnerability. If we consider the pin pad as a graph, all the keys, the node of the graph, are fully connected. In fact, when I digit, for example, the key 1, I have no restriction to press any other key on the pin pad. I can digit 1, 1, 1, 2, 1, 3, and so on. What is different between these couple of keys is their physical distance, or in a graph, the weight of the edge connecting the nodes. From that, we identified 8 classes of distance. The first is distance 0, so the key pressed are the same, like 1, 1, 2, 2, 0, 0, and so on. Then we have distance 1, so like 1, 2, 1, 4, but also 2, 5, 8, 0. Distance 2, so 1, 3, 1, 7, 2, 8. Distance diagonal 1, like 1, 5 or 5, 9, 9, 5. Distance diagonal 2, so 1, 9, 7, 3. Distance diagonal small, like 1, 8, 2, 9, 4, 0. Distance diagonal long, like 1, 0, 0, 1, 0, 3. And final distance 3, that there is no connection from key 1, but is present only between 2 and 0. So this is the graph with all the connections starting from each keys of the pin pad. But we asked, how much does the knowledge of the distance affect pin security? And this has been treated in this work, Pilot, and how we can see this figure compare the difference of pins recovered if the attacker knows the physical distance of subsequent keys and the random guessing. As we can see, if the distance is known, the attacker can recover 18% of the 4-digit pins in 5 attempts, against the 0.05% of random guessing. But knowing the physical distance between keys poses another significant security problem. A fundamental security factor in pins is that their distribution must be uniform. Otherwise, an attacker could make a statistical attack and have a considerable advantage with little effort. In this case, the knowledge of physical distance unbalances the distribution by creating less secure pin subsets than others. So, for example, let's see in this figure that pin 1212 can be guessed in 128 attempts on average, while pins 1220 can be guessed just in 2 attempts. The knowledge of the physical distance between 2 keys is difficult to have for an attacker. But we're wondering, is it possible to deduce the distances between keys using environmental information? So, for example, if the screen is visible, we can record the asterisk sequence on the screen. And maybe the inter-keystroke timing correlates with the physical distance. That was demonstrated in Pilot. But also the audio signal can be used to get a lot of information about the sequence of the key pressed. Usually, pin pads, for usability reasons, have feedback sounds, a beep that can be well recognized. This can be leveraged to extract the inter-keystroke timing between subsequent keys. To test our hypothesis, we set up an experiment with 22 participants who have to digit a series of 4-digit pins. Pins were selected to cover all the possible distance and were 42 in total. Here is the process that we used to extract inter-keystroke timing. and how we identify the peak of each key pressed. So first, we normalized the audio signal in an interval of -1 and 1. Then we applied the bandpass filter to isolate the characteristic frequency of the feedback sound. We then set all the samples of amplitude below 0.01 to 0, and finally we extract the maximum samples amplitude in a sliding windows of 1200 samples. From that we extract the peaks and we evaluate the timing distance between peaks. Here we can see the error of inter-keystroke timing extraction between audio signal and video. As we can see, the sound is more precise than the video, and this is basically due to the sample frequency. The monitor has a refresh rate of 16 Hz usually, while the camera that records usually at 30 frames per second, while the audio is recorded at a frequency of 44 kHz, and the sound in a real environment is continuous. We modeled the inter-keystroke timing using gamma distributions. In total, we built 8 models, one for each physical distance. Gamma distributions are commonly used in literature to model reaction times, and in a certain sense, even inter-keystroke timing can be considered as reaction times. The structure of the systems work like this. We splitted the dataset, where 11 participants were used to fit the gamma distributions, while the other 11 were used to test our system. We extracted the inter-keystroke timing from logged timestamp, audio, and video, and we deduced the distance between subsequent keys from the models. Then we passed the distances to the pin guesser, which is an algorithm that gives in output the probability of each pin based on the inter-key distance. The pin guesser algorithm can also receive as input other additional information about user behavior or pin, and provides in output a list of the most probable 4-digit pins. Results show that audio and logged time perform similarly, while the video is less accurate, as we expected for what we said before. However, leveraging audio signal, we were able to guess 4% of pins within 20 attempts, with a 20-fold improvement compared to random guessing. Then we wondered if there were other ways to get usable information about the pin or the distance between keys. For example, does the way we type the pin provide useful information? We analyzed how users type the pin, and we divide them into single-finger typists and multi-finger typists. Single-finger typists represent the 70% of the total. Our idea is that if I type using just a finger of one end, the inter-keystroke timing should correlate better with the physical distance between keys. And that's exactly what happened. We can see from the figure how single-finger typists are more vulnerable to our attack compared to multi-finger typists. So there is a correlation between distance and pin entered method. As we saw, the user behavior affects the guessing probability of the pin. But then we wonder, can we get information even after entering the pin? For this purpose, we used a thermal camera that can be purchased at a low price to evaluate its trace on the pin pad. The thermal camera can also be used with a common mobile phone. This is what the camera sees on a plastic pin pad. The persistence of the heat trace varies depending on the material of which the pin pad is composed. For example, metal dissipates heat very quickly, but an attacker can apply films, like plastic films, to the keypad to thermally insulate it. And these are the pins recovered with a thermal attack in red compared to the pin recovered merging thermal traces and inter-keystroke timings. Here, the attack becomes much more effective. In fact, we can get about 34% of the 4-digit pins within 3 attempts. So to summarize, in this work we have identified 4 possible information classes that can be exploited by an adversary: the inter-keystroke timings, the typing behavior of the user, the knowledge of the digit of the pin, and the knowledge of pin's digit. In this table we summarize how much each knowledge affects the attempts to guess a 4-digit pin, and how the combined use of one or more information can considerably increase the accuracy of the attack. The inter-keystroke timing deduced from the audio increases guessing performance of other sources of information readily available to the adversary. When the adversary was able to observe the first or the last digit of a pin, inter-keystroke timings further increase the number of pins guessed within 5 attempts by 14 times. If the adversary was capable of observing which keys were pressed to enter a pin, for example using a thermal camera, adding inter-keystroke timing information allows him to guess 15% of the pins within a single attempt. This corresponds to a 4 times reduction in the number of attempts compared to knowing only which key were pressed. So to conclude, in our work we demonstrate that inter-keystroke timing can be accurately derived from audio and can be used to significantly reduce the attempts to guess a pin. Moreover, compared to other sources like video, keystroke timings deduced from the ATM feedback sounds are easier to collect. Our results show that users who type pins with one finger are more vulnerable to pin guessing from inter-keystroke timing. The knowledge that the user is a single-finger typist leads to 34-fold improvements over random guessing, when the adversary is allowed to perform up to 5 guessing attempts. Finally, we showed that inter-keystroke timing can be combined to other information, improving significantly the performance of the attack. So that's all. Thank you for watching. If you want to contact me, please send an email to matteo.cardaioli@phd.unipd.it.